This video is about signs, properties, and fundamental identities of trigonometric functions. And by signs, I mean S-I-G-N-S, as in plus or minus, positive or negative, not S-I-N-E, the sign function, which is one of our trig functions. As always, read through the textbook carefully and take good notes, but now consider the following highlights. Let's recall our 6 trigonometric functions that we've already defined in our previous lesson. To bring those back in, we're recalling that we have real number t, which we've modeled as an arc starting in standard position, which is the point 1, 0 on the right side of the unit circle, and then extending from that starting point counterclockwise around the unit circle until it gets to its terminal or stopping point, which we'll call P, and that point P has a coordinate address of x, y. And using that x and that y, we've defined 6 trigonometric functions already. Now they come somewhat in pairs because of the fact that x and y are used to define them. For example, sine of t equals y, and then cosecant of t equals 1 over y. So you can see the reciprocal nature in those functions, the way they're defined. Of course, we can't divide by 0, so anytime we have a variable in the denominator, we have to restrict it so it's not 0. Another similar pair would be cosine and secant. So we define cosine as x, or in other words, cosine of t equals x. T is this arc input, and then secant of t is 1 over x. So there's the reciprocal of the x. Again, can't divide by 0, so x cannot be 0 for secant. And then thirdly, tangent and cotangent, where we define tangent of t as y over x, can't divide by 0, and cotangent over t as the reciprocal, which is x over y, can't divide by 0. Okay, so we're seeing how these are not only defined previously, but now, again, just using x and y from the coordinate plane. This can help us understand some more properties about these kinds of functions. One such property to observe would be the signs, and that is S-I-G-N-S, again that's plus or minus, positive or negative, of these trigonometric functions, which correspond with the signs of, well, x and y in the coordinate plane, because that's exactly how these functions are defined. Every one of these 6 trig functions is defined in terms of x or y or both x and y. So let's recall some things about the coordinate plane that we already know from algebra. As we've already been discussing and using, we have a horizontal axis, which we call the x-axis. We have a vertical axis, which we call the y-axis. And then we have, in a result of that, 4 quadrants. And so the upper right zone we call quadrant 1. The upper left zone we call quadrant 2. We usually use Roman numerals to denote these. The lower left zone we call quadrant 3. And then the lower right zone we call quadrant 4. Now, if we consider the nature of x and y in the coordinate plane, then let's recall again what we already know. To the right of the y-axis, we have, well, quadrant 1 on top and quadrant 4 below, and in that half of the coordinate plane, we would say that the x values are all positive. They're all to the right of the y-axis. And that's in correspondence with the number line that we use for these axes. Or similarly, we would say that above the x-axis, so that would be in quadrants 1 and 2, we would say that the y values are all positive there. And of course, correspondingly in the opposite zones for each, they would be negative. So with that in mind, we could summarize where certain things are positive or negative. So for example, in quadrant 1, we have x positive and y positive. Or in quadrant 2, we have x negative, y positive. And there's just combinations of these going all the way around the quadrants. In quadrant 3, they're both negative, so we'd say x is less than 0 and y is less than 0. And then in quadrant 4, we have x positive, so x is greater than 0, and then y is negative, so y is less than 0. Well, with those signs, that is SIGNS, positive or negative nature, for x and y in view, and since all 6 trig functions are defined in terms of x and or y, we should be able to tell exactly where any of those trig functions are positive or negative directly, corresponding to those signs of x and y. So that's helpful in understanding the nature of where our trig functions will be on the coordinate plane. Next, let's recall the full unit circle with special arcs and terminal points that we've already been looking at in previous lessons, and observe how the signs of the terminal point coordinates align with the appropriate quadrants of the graph. And so as we just observed, of course, we can split this into 4 quadrants. We have quadrant 1 in the upper right, we have quadrant 2 in the upper left, we have quadrant 3 in the lower left, and quadrant 4 in the lower right. And because of that, and the signs, SIGNS, of the coordinates in any of those quadrants, which we just reviewed, we would expect to see that showing up in the unit circle terminal points with the coordinates of those points. And sure enough, this is exactly the case. In quadrant 1, we would expect for cosine of t to be positive and for sine of t to be positive. And again, that's corresponding to the fact that x is positive and y is positive in quadrant 1. And sure enough, if you look at every one of the coordinates of the terminal points in that quadrant, you can see they're both positive, x and y. Or similarly in quadrant 2, we would expect to find that the cosine, which of course is the x value, would be less than 0 because you're to the left of the y-axis. But then in quadrant 2, we're above the x-axis, so we would expect that the sine of arc t there would be positive. And sure enough, if you look at carefully all those points, the terminal points in quadrant 2, you can find that all the x's are negative and all the y coordinates are positive, corresponding again with the sine or cosine of arc t. And then just to review, remember arc t is some arc that would be starting from, let's say, the right side of the graph at 1, 0, and then extending from there counterclockwise to wherever it needs to stop according to the given input. So if it rotates counterclockwise from the point 1, 0 up toward and then stops at pi over 3, which is one of our special arcs, then that would be where t equals pi over 3, and there, of course, the terminal point would be in quadrant 1. You'd find its x and y coordinates both to be positive. This is all fitting together. If we continue around the circle, or maybe go the other way, so let's now also review the fact that we've discussed negative arcs. So what if we started one still at 1, 0 on the right side, but then extended it clockwise, so now downward, and let's just go down maybe halfway through that first quadrant, which is actually quadrant 4 on the bottom right side. So let's say starting at 1, 0, extending downward clockwise into the middle place of that quadrant. There you would find that you could describe the arc as having a value, a t value of negative pi over 4. And negative means it goes in a clockwise direction. Where it stops down there, of course, you have a terminal point with an x value that's positive, y value that's negative, and that actually fits with what we expect given that we are in quadrant 4. So you can start to see how really the details of the unit circle and what we know about it so far algebraically make plenty of sense according to the coordinate plane. And then if we define trig functions according to x and or y, then the signs of those trig functions could also correspond exactly in the same way. Okay, so let's move on and discuss a little bit further here. There's something else we can review from algebra called the even and odd properties of these trig functions. So in algebra, you may recall having even and odd functions. Let's recall. So in algebra, when we say that an even function is what we're working with, what we mean is that f of negative x equals f of x. A visual way to see this, as you may recall, would be symmetry about the y-axis. So if you fold your paper on the y-axis, like left to right or right to left, then the graph on one side would land exactly on the graph on the other side. They would match exactly with symmetry about the y-axis. That's what an even function has. Or an odd function is defined where f of negative x equals negative f of x. So now it's the opposite of f of x. And in this case, there is still symmetry, but it's symmetry about the origin, which is like two flips, maybe horizontally and vertically flipping over. So if you fold the paper twice, then the graph would land on the other part of it that matches exactly. Well, because of all that and the way we've defined our trig functions, turns out some of them are even and some of them are odd. So we have even functions in our trig family, and those would be cosine and secant. And so in other words, based on the definition of even and odd, cosine of negative t is the same thing as cosine of t. And that just fits this definition of even function. Or similarly, secant of negative t is the same thing as secant of t. Now, if that seems a little strange, we'll see more and more examples of this to see how it actually does fit and work. Moving over, though, to the odd side of the family. So odd functions in the trig family would include sine, cosecant, tangent, and cotangent. For all these odd trig functions, we could say that a negative with the input kind of pops out in front of the output, making it negative. So sine of negative t equals negative sine t, cosecant of negative t equals negative cosecant of t, and so on. Tangent, cotangent, same thing. You have a negative sign that shows up in front of the result on the opposite side where the output would be showing up. Let's take a look at some examples where we want to find the exact value of the trig function at the given input. So in some sense, this is actually just some review, and we're going to use the unit circle for it. Now I'm going to redraw a mini copy of it. I think it's good to get in the habit of being able to do this by hand. We have the unit circle printed above. We'll refer to it as needed, but eventually you're going to want to be able to draw and reference it quickly with the patterns we know of it. So in this first example, we're trying to find the exact value of the sine of negative pi over 3. Now, there are a couple ways to do this. What we discussed previously, even earlier in this video as I reviewed, or in previous lessons, is that a negative input is like just going in a clockwise direction. So that could be done here to find where the terminal point is for negative pi over 3. However, we could also use the odd-even property here, and since sine, if you look at our list above, is an odd function, this means that the sine of a negative input, which is what we have, sine of negative pi over 3, would be equal to negative sine of positive pi over 3. And so this is just following exactly with the odd definition for sine that we already have. And the point here is that you can then find maybe a more familiar positive input, pi over 3. So if we start at 1, 0 on the right side, and we extend a positive pi over 3, of course that would be up in quadrant 1, we could find the y value there. So if we're using this modified version now, and its input, which is now positive pi over 3, then we would say our arc value for t is positive pi over 3, and that puts us in quadrant 1. Of course, we know that from our unit circle, the y-coordinate at the terminal point for pi over 3 in quadrant 1 would be root 3 over 2. However, since we used the negative identity with this sine function, which resulted in a negative sign in front of the function, that means we would make the result actually negative root 3 over 2. And so that's corresponding exactly with what the sine output is, what the sine value is, when the input is negative pi over 3, which happens to be the same as the negative sine of positive pi over 3, given the odd-even identity. Or let's try another one. Suppose we have secant of negative pi over 3. Again, you could consider a negative input as an arc that starts at 1, 0, but then rotates in a clockwise direction. Or we could recognize that with our odd-even properties, and secant being an even function up in our list, then secant of a negative value would be equal to the secant of the positive of that exact same input. So in other words, secant of negative pi over 3 is equal to the secant of positive pi over 3. And again, that's using just the odd-even property we have defined above. So we can then start over and just keep things simple and positive. If you're trying to find the secant of pi over 3, you've got to figure out where that goes. Well, it's in quadrant 1. Pi over 3 would be, if you're counting from 1, 0 and the starting point, counterclockwise direction, it would be the third tick mark in quadrant 1. And so let's mark this up a bit here. We have, we have a t value of pi over 3, and then the secant value there, let's recall, secant would be 1 over x, which means we want 1 over the x coordinate of that terminal point. Well, the terminal point where pi over 3 stops in quadrant 1 would be 1/2 comma root 3 over 2. It's getting kind of small here to write. Okay, so, but if I want the x coordinate for 1 over x, and that happens to be 1/2, then I could say this is really 1 over 1/2, which is the same thing as 2. And so here we have examples of using the negative identities to find exact values of given trig functions and inputs. Okay, let's move on and now discuss some fundamental trig identities, which is really just a way to summarize or describe things we've already been discussing. And this is all built on the way we've defined our 6 trigonometric functions above, and we've used those in terms of x and y on the terminal point coordinates, but here we're going to use them in terms of just actual trig functions. So since secant of t, if you go back to where we defined this, way above, where we recalled the originals, secant of t we said was 1 over x, okay? But if x is really just cosine of t, then we can substitute and write one of those for the other. In other words, we could say secant of t is 1 over cosine of t. We're just replacing the x with cosine of t, which is what it is. Or similarly, cosecant of t, this would be defined as 1 over y above. Well, if y is really sine of t, then we really have 1 over sine of t. So cosecant of t is 1 over sine of t. Or similarly, tangent of t, we defined above as y over x. So that would be like saying sine of t, which is what y is, over cosine of t. Or, in the same kind of way, cotangent is really the same thing as 1 over tangent of t. And that's just the reciprocal of it. Well, if tangent was sine over cosine, then cotangent would be the opposite, cosine over sine. Or reciprocal, not necessarily the opposite, the reciprocal. Okay, so we flip that over. And that's how we can define some what we'll call basic reciprocal identities using these trig functions. Now, there's even more we could do with this, so let's think carefully about what we already know. Recall that We already know the unit circles equation, as we discussed early on. The unit circle is what we're doing to kind of build and understand how all this stuff fits together. And its equation, as reviewed previously, is x squared plus y squared equals 1. That's just a standard equation of a circle with a radius 1. Okay, well, let's now extend this a little bit with some of the trig identities and definitions we have building with us. If we know that x squared plus y squared equals 1, and we know that x is really cosine of t and y is really sine of t, then we could write the following basic Pythagorean identity. Cosine squared of t plus sine squared of t equals 1. Now, that is the basic Pythagorean identity, and the reason we know this works is because, again, cosine really represents x, so it's like saying x squared plus, and then sine is really like y, so x squared plus y squared equals 1. That's just the equation of the unit circle, but now written in terms of trig functions sitting in for x and y. Now, in terms of notation, I can't recall if we've seen this quite yet or not, but to square a trig function, there's a way we do that as I've written it. So for cosine of t squared, we can square or put the square symbol, that is the exponent of 2, just above the actual s for cosine, so it looks like cos squared and then the t's after that. That's the same thing as like saying cosine of t squared. But it's just a convention to write it that way, I think, for convenience. So in other words, if I had cosine, that is cos, of t is my input arc, right? If I were to square the whole thing, maybe like if it were in brackets or parentheses and I squared the whole thing, that's the same as squaring it right after the s, as we've noted above. So where we put the square is about the same. Now, the reason we would want to put either brackets or parentheses or put it with the s and not the t without the brackets or parentheses is because then it can get confusing, like are we squaring just the t or the cosine of t? And so these kinds of notation conventions will be helpful to understand, and we'll see them used frequently. Okay, now here's what's nice about the Pythagorean identities. You can easily go from one to another with some simple adjustments. So here's what I mean. If we start with the basic Pythagorean identity, and that is cosine squared plus sine squared of t equals 1, and of course that's interchangeable in terms of the order. You could also say the same thing as sine squared of t plus cosine squared of t equals 1. Addition is commutative. So you could put the cosine or the sine first, doesn't matter. But if we did some basic operations with that exact identity, we would get some other interesting things. So now let's try a little adjustment. Let's try dividing by sine squared of t with that original Pythagorean identity. So if I do that, we would end up with sine squared of t plus cosine squared of t equals 1. But if I'm dividing everything by sine squared of t, then I would have sine squared of t over sine squared of t plus cosine of squared of t over sine squared of t equals 1 over sine squared of t. Now, why does it matter and what's going on? Well, take a look at this carefully in terms of algebra. What is sine squared of t over sine squared of t? Well, 1. What is cosine of squared of t over sine squared of t? Well, think about this. Isn't that the same thing as cosine of t over sine of t all squared? Algebraically, that exponent would follow the exponent rules to be squaring each of those, top and bottom, with the fraction. What is cosine t over sine t? It's a familiar identity for us. Cosine t over sine t is really cotangent of t. Okay, more on that in a second. If we move on to the right side, we have 1 over sine squared of t. Well, again, that's like saying 1 over sine of t squared. And what is 1 over sine? Well, it happens to be cosecant. So what we get is a different identity that's just kind of rearranged. We really now have 1 plus cotangent squared of t equals cosecant squared of t. 1 over sine is cosecant, so 1 over sine all squared is cosecant squared. And so what we have is what you could call another version or form of the Pythagorean identities for trig functions. And so if we start with the basic one of sine squared plus cosine squared equals 1, and then simply divide everything by sine squared, we get another form of a trig identity. Well, as you could probably guess, we could get something similar but different if we tried dividing by cosine squared. So now let's say this, try dividing by cosine squared of t, that is from the original, and what we end up with, of course, is sine squared of t plus cosine squared of t equals 1. But if I divide everything by cosine squared, one term at a time, then what do we have? Well, the first term would be sine squared over cosine squared, which you may recall as tangent squared, right? So we could say this is really, I'll just write the final version here. This is really tangent squared of t plus 1 for the middle term, cosine squared over cosine squared, equals, and then 1 over cosine squared of t, again go back to the definitions, that would be secant squared of t. And so we're getting another form of the Pythagorean identity. So we have three, really two coming from one of them, the first one. And these are all useful, as you will see going forward in this class, but these are part of what we'll call Pythagorean identities. Okay, let's try to apply some of this with one more example, which says this. Write the first expression in terms of the second if the terminal point determined by t is in the given quadrant. And then what we're given in this is the first expression is secant of t, second expression is tangent of t, and we're in quadrant 2. So if we're supposed to write the first expression in terms of the second, in terms of means like solved for. So we want to have the first expression solved in a way that it's by itself, and on the other side of the equal sign you see the second expression, which means we want secant solved, so it's a secant of t by itself, and then it's equal to something that's going to involve tangents. And then we'll see why this quadrant specification, quadrant 2, might matter. So let's look back through our trig identities that we have so far, the Pythagorean identities, and look for one that involves secant and tangent. You will find exactly one that does. So we know so far from exactly what we did before that secant squared of t is equal to 1 plus tangent squared of t. And so there is us writing secant squared in terms of tangent squared, but that's not quite what we're asked to write. We want to write the first in terms of the second. This is not quite the first. This is secant squared, and they gave us just secant as the first one. So the question is, how do we solve for secant if we have secant squared? Well, we could just take the square root of both sides of this equation. We'll do that. The square root of secant squared of t we could write as just secant of t, with the cost of now having to put a plus or minus on the other side in front of that root. You may recall from algebra, when you take the square root of both sides of an equation, we have to throw in a plus or minus, which accounts for the algebra behind the scenes there, the absolute value that's actually showing up. but it's accounted for with the plus or minus. So really we have secant of t equals plus or minus, and then we have our expression as given, which is 1 plus tangent squared of t. That's what we had already solved in the previous step. Okay, so we've written the first expression, that's secant of t. In terms of the second, which is tangent, because now the right side has just a tangent. Now it's a tangent squared, that's fine. And more specifically now, though, we're in quadrant 2. So let's recall what this might mean. In quadrant 2, if you take a look back at our axes, quadrant 2 is the upper left zone. And in that place, we know that the x values are negative and the y values are positive. So what does that mean? Well, secant is really 1 over cosine. If you look above at our definitions, or in other words, 1 over x, as we've defined it. And because then x is negative in quadrant 2, I'll just kind of note, remember, this is really 1 over x. And since x is negative in quadrant 2, that means the secant will also be negative, which means we're going to use that form of our answer options. So let's summarize this with one clean answer. We could say that really secant of t is equal to negative square root of 1 plus tangent squared of t. And that's writing the first expression in terms of the second one, given the quadrant that we're in.